This presentation is about our work on motion planning for variable topology truss modular robot. A variable topology truss, or a VTT, is a very different modular robot which is a reconfigurable truss. An individual node can be split into two separate nodes, and inversely, two nodes can be merged into one. This process is a topology reconfiguration. The position of a node can be changed by changing the length of connected members. That is similar to controlling a parallel robot, and this is the geometry reconfiguration. We use a non-directed graph to model a VTT. For any node, its configuration space is clear R3, and the state of each member is determined by the locations of its two nodes. In order to do path planning for a node, we present a fast algorithm to compute its obstacle region and free space. In our previous work, we have shown that the obstacle region of a node is composed of multiple polygons. Then, with all obstacle polygons, we can finally find its free space on the right using a boundary search algorithm. The node V0 can move freely to any location inside the space without collision as long as its path is inside the space. We extend this work to compute the configuration space for a group of nodes. A group contains at most two nodes. We ignore the collision among members controlling the two nodes, and in this case, the collision region for this group is determined by all still members. For example, for node V0 and V1, we compute the obstacle region of V0 with all yellow members being ignored. Similarly, we compute the obstacle region of V1 with all green members being ignored. Then we can search the free space of each node. We constrain the motion of the two nodes to be inside the two spaces respectively. If V0 and V1 are not connected, we only need to consider the collision among these colored members. Otherwise, we also need to consider collision between the member connecting them and other still members. In this way, the motion can be validated easily and efficiently. For example, we want to do planning for node V0 and V1. We first compute the group free space for each node, and the motions of V0 and V1 are constrained inside the group free space, and only collisions among green and yellow members are possible. Motions can also be checked and validated efficiently using our previous work. Now we can do motion planning for a pair of nodes efficiently using a group of free space. For a geometry reconfiguration task, multiple nodes are involved. Given a set of nodes for moving, we first divide them into multiple groups randomly, and each group only contains one or two nodes. Then do planning group by group. For each group, we will compute the configuration space for this group and apply RLT to do path planning. All samples are generated inside the group free space, which makes the planning very efficient, and motion validation is also simple and efficient. This is our geometry reconfiguration test with 4 nodes involved. In this video, we move V3 and V5 first, and then V1 and V6. We ran this test for 1000 times, and the average running time is around 0.8 seconds, and with standard deviation being around 0.6 seconds, and the success rate is 100%. The next part is about topology reconfiguration. The free space of a node is usually divided into multiple enclosed subspaces by obstacle regions, and if the node wants to traverse from one enclosed subspace to another, topology reconfiguration is needed. For example, here is the enclosed subspace containing the current position of node V0, and here is another enclosed subspace for V0. In total, there are 33 enclosed subspaces above the ground. If V0 wants to go to any location inside the triangular pyramid subspace, we need topology reconfiguration. These enclosed subspaces can be found by repeatedly applying our boundary search algorithm along obstacle polygons. When doing topology reconfiguration planning, we first compute all the enclosed subspace for a given node, then randomly and uniformly pick a position for these enclosed subspaces. And if there exists a way to split the node into two such that this node can go from one enclosed subspace to another one, then the two enclosed subspaces are adjacent. For example, in this 2D case, here is a yellow obstacle, and the red node is controlled by 4 actuators. The node cannot go beyond these blue dashed lines, so there is no way to go to this green location. However, we can split this node into two so that the blue dashed line boundary disappears, and these two new nodes can approach the green location and finally merge there. Using this idea, we can apply a graph search algorithm based on directory algorithm to explore these enclosed subspaces to find a sequence of topology reconfiguration actions. And we can use geometry reconfiguration for motion planning after splitting the node to go to an adjacent subspace. This is a test from our IROS work, and our current approach can solve this problem much faster, and the performance is shown in the table. This is a more difficult test that we need to reconfigure a node twice in order to go around the obstacles. We tested this one for 1000 times, and the performance is shown in the table. Thank you for watching.